Hello everyone. Today we're looking at symmetry. Now symmetry is something we might have covered previously in middle school. We're going to go over the same general material and add a little bit to it. So first off, some definitions. Two-dimensional figures have what is known as line symmetry, in that the figure can be mapped onto itself by a reflection within a line known as the line of symmetry. In a similar fashion, a figure can be said to have rotational symmetry if there exists a possibility for the figure to be mapped onto itself by some rotation between 0 and 360 degrees around or about the center of a figure, known as the center of symmetry. So for my examples here, I'm going to state whether or not the figure in example 1 appears to have line symmetry. If so, I'm going to draw all lines of symmetry and state their number. Well, if you take a look at that heart, the heart has line of symmetry, but it only has the one line of symmetry going through here. It doesn't have symmetry along any other possible line. So the heart has line symmetry, it has one line of symmetry. Example 2, state whether the figure appears to have rotational symmetry. If it does, locate the center of symmetry and state the order and magnitude of symmetry. Well, this figure seems to be able to rotate 4 times around itself and will still have the same figure. It's mapping onto itself. As such, the figure has order 4 symmetry and a magnitude of 360 divided by 4, also known as 90 degrees. To get the magnitude of any sort of rotational symmetry, we're going to take 360 and divide it by the order of symmetry. That will always give us the magnitude. The center of symmetry is going to be the intersection of the diagonals, right there. Let's take a look at some practice problems. Numbers 1 through 3, we're going to state whether the figure appears to have line symmetry. We'll write yes or no, and if it does, we're going to draw all lines of symmetry and state their number. So number 1, we have here a pentagon. Now I know that if I go from my vertex up here and draw a line straight down, I have a line of symmetry because this side can fold over to that side. If I actually do that for each of my vertices to the opposite sides, like so, we end up with 5, forgot one. We end up with 5 lines of symmetry. So yes, it has lines of symmetry. There are 5 lines of symmetry. Smiley face. Well, if I draw a horizontal line, I'm not going to have any symmetry because if I fold it over, the eyes and the mouth won't match up. If I draw a diagonal line, they won't match up. Other diagonal line, they won't match up. But if I draw a vertical line, like so, my left side will match up with my right side. So I do have symmetry, and I have one line of symmetry. The letter Z. So let's take a look at some lines, possible lines. If I draw a vertical line down the middle, try to fold it over on itself, it's not going to work. No symmetry there. If I do a horizontal line, no symmetry there, because this part won't match up with that part. If I do instead a diagonal line, that won't work. Diagonal the other way, that won't work either. So this ends up being no symmetry. None. Nada. Zilch. 4 through 6, I want to state whether the figure has rotational symmetry. That is to say, can I rotate it around itself to end up with the same figure? Write yes or no, and if it does have rotational symmetry, locate the center of symmetry, state the order and magnitude of symmetry. So number 4, I've got a, what's this? 1, 2, 3, 4, 5, 6, 7, 8-pointed star, 8-pointed sun, perhaps. And I know that if I rotate it a little bit, if I rotate from one point to the other, I'm going to end up with the same image of itself. So does it have rotational symmetry? Yes. Yes, it does. What magnitude does it have? Well, how many rotations can I make and get the same image? 1, 2, 3, 4, 5, 6, 7, 8. So 8 magnitude. And then for my, 8 for my order, magnitude of symmetry, well, that's going to be 360 divided by 8 to give me 45 degrees. So a 45-degree magnitude of symmetry. Number 5. Oh, I need my center, don't I? Center symmetry is going to be the center of my figure, approximately there. Number 5, we want to try to rotate it around. But if we rotate it around, say 90 degrees, we're going to end up with a telephone-looking thing, which doesn't work. If I rotate it 180 degrees, end up with something like that. 270 degrees, going to end up with something like that. So no matter how I rotate this, I'm not going to have any sort of rotational symmetry. So does this have rotational symmetry? No, it doesn't. Number 6, we have a flag. We want to figure out, does it have rotational symmetry? Well, if I take my flag and I rotate it 180 degrees, I'm going to end up with the same figure. But I have to rotate it 180 degrees to do so. As such, I know that I have that symmetry, and I know that my magnitude of symmetry is 180 degrees. So I can work backwards, if I need to figure out my order of symmetry. Because my order of symmetry, well, that would be 360 divided by my order will give me my magnitude. Rewrite the equation. 360 divided by my magnitude gives me my order of 2. As for my center of symmetry, there. All right, so that's the first page. Let's go ahead and look at three-dimensional figures. So three-dimensional figures are going to follow similar rules, just in 3 dimensions. So a three-dimensional figure is said to have plane symmetry. Don't know why it keeps being so big. Said to have plane symmetry if the figure can be mapped onto itself by reflection in a plane. So planes being that thing from way back when in chapter 1 that's infinitely long in 2 dimensions that essentially slices through space. If we can find some plane that will slice through our object to give it symmetry by reflecting across that plane, we have plane symmetry. Whereas axis symmetry occurs if the figure can be mapped onto itself by rotation along some axis, some line between 0 and 160 degrees. So in fact, it's the same as our terminology for 2 dimensions, just booted up 1 dimension. What was previously a line of symmetry got upgraded to a plane of symmetry. And what was previously rotational symmetry has become axis symmetry. But overall, it's the same general concepts. We're looking for ways to make our figures symmetrical. So, example A, state whether the figure has plane symmetry, axis symmetry, both, or neither. So if we look at it, we have some cylinder. Well, that cylinder has a central axis that we can draw a line through and rotate around that center. No matter how much we rotate it, we're going to still have the same general figure. It also has some plane that we can use to cut up our figure to reflect the figure across that plane to give us plane symmetry. So the cylinder has both plane symmetry and axis symmetry. Meanwhile, the letter N only has plane symmetry. Because it's 3-dimensional representation of the letter N, we can take a plane and cut it into the height of our N to essentially give us symmetry along the plane. But there's not any sort of line that I could draw, any sort of axis I could draw, for which I could rotate around that axis and get the same figure. So it has plane symmetry, but not axis symmetry. So as far as our exercises go, 6 of them, 6 figures. We want to state whether each figure has plane symmetry, axis symmetry, both, or neither. We're not going to be drawing in the lines. We're not going to be rotating ourselves. We just want to identify if it has plane, axis, both, or neither. So figure 1. It's a prism, hexagonal prism. A hexagonal prism has the axis at the very middle, such that I can rotate it 6 times specifically to get symmetry along itself. So I know it has axis symmetry. But I also know that I can draw a horizontal plane or a vertical plane such that I could reflect it across itself along the plane. So this first one actually has both plane and axis symmetry. This sphere, 3-dimensional circle essentially, think of a ball if you will. Well, here we have some plane that I can use to divide my figure into a top and bottom, a northern hemisphere and a southern hemisphere if you will, with that equator being our plane of symmetry. We also know that we can spin a ball along some axis, such that the ball will essentially keep the same face. So this ball, this sphere, has both plane and axis symmetry. Number 3, we have this 3-dimensional room thing. Unfortunately, I can't spin this in any way, shape, or form to end up with the same figure because of this missing component here, this missing block here. But I can still draw a plane to cut through this to give it plane symmetry. Therefore, number 3 only has plane symmetry. Number 4, it's a similar case. We got this crescent moon here. I can draw basically a line to cut through this plane. Sorry, I can draw a plane to cut through this figure like so, such that it will be symmetrical with itself. But there's no point that I could rotate it around itself to end up with the same figure. If I rotate 90 degrees, my crescent moon will be like that. Rotate 90 degrees again, I'll get it like that. 90 degrees again, like that. But none of those are the same general figure. So this crescent moon that we have here, it will have plane symmetry, but it will not have rotational symmetry or axis symmetry. Number 5, we have a trapezoidal figure. There does exist an axis that I can spin it around and get the same figure. If I spin it around 180 degrees, I'll get the same figure. And there's also a plane that I can cut through on that same token, such that my right side and my left side are reflections of each other. So since this has both plane symmetry and axis symmetry, I write both my answer choice. Number 6, rectangular prism. Well, I do have an axis here that I can rotate such that I can get the same figure. And I also have a plane that I can cut through to get the same figure on left and right. As such, this has both plane symmetry and axis symmetry. And that's about it for the notes. If you have any questions, please shoot me that email, ask during class, or ask during tutoring.